In this video, we're going to take a look at how we can use the MSP to figure out the KSP for a substance. So here we have a scenario where 0.00172 grams of PbI2 will dissolve in 100 mils of water. What is the KSP? So what we're essentially telling you is enough information to find the MSP, and then using the MSP, we want to figure out what the KSP is. And that's a bit confusing when nothing is written down. So let's just start with something. Usually, the best thing to start with is making your dissociation equation. So we saw the dissociation equation in previous videos. If you don't remember how to do that, please make sure you check those videos out. So we have a PbI2 solid. Make our equilibrium arrows. We'll get some Pb2 plus AQ plus some I minus, and since there's 2 I minus AQ. And what we can do with this is we could actually create an ice table, because whenever we want to find the K value, we need an ice table to show what the concentrations at equilibrium are going to be. So let's go ahead and do that. We're going to have I, C, E. And generally, remember when you have an ice table, you need to have some initial concentrations given to you. Now, assuming that we just have a beaker of, let's say, pure water over here, at the very beginning of this process, if you only have pure water here, pure H2O, you don't have any of the ions present, right? So you have 0 of this and 0 of this. And you can kind of treat this like you would any ice table based on the molar coefficients. We know that over time, you're going to get plus x over here and plus 2x over here. And at equilibrium, you'll have x and 2x. And then over here, of course, you're going to have minus x. The problem is we don't know what the initial concentration is. Technically speaking, a solid can't be, you don't have concentrations, the concentration of solids don't need to be tracked in the ice table because the concentration won't change. But we're going to treat the initial concentration as being the MSP. So MSP is actually going to be our initial concentration. So when you first throw this into water, what is the initial concentration going to be? We're going to treat that as our MSP. So we're going to go ahead and do that. We're going to say we have MSP. This is the maximum that will dissolve in the volume of water given. We're going to put that into our initial concentration value. So let's go ahead and do that. We're going to find out what the MSP is first. So I'm going to carry this step out just over here off to the side. So remember that the concentration is equal to N over V, and that's going to be our MSP. So we have a volume of 100 mils, right? This is 100 mils. But remember, in liters, that's 0.1 liters, so 0.1. And we need to figure out the number of moles of PbI2 that we have. So just to show you that works, let's just go ahead and do that. So this is volume is equal to 0.1 liters. Moles is equal to mass over molar mass. And so we have 0.00172 grams divided by the molar mass of PbI2. So I need to go to my periodic table because I don't remember these molar masses off the top of my head. So PbI2, Pb is, 207.2, so 207.2 plus 2 times whatever iodine is. So iodine is 126.9, 126.90. And we get 461.00 grams per mole. Cross out the grams, and we're left with moles. So that's 0.00172 divided by that molar mass we just said, and we get this very, very, very small number of moles, and that's okay. That means it's not very soluble, 0.00172 0.0003731 moles. You could also write that in scientific notation if you wanted to. So you could say 3.731 times 10 to the power of negative, negative 6 moles. And we'll divide that by 0.1, and we get 0.0003731 moles. In other words, 3.713 times 10 to the power of negative 5. So that's our MSP. And we can put that over here. 3.731 times 10 to the power of, oh, that's not moles, sorry, moles per liter, right? Because we divided by volume. That's a concentration to the negative 5. And then we're just going to make a note that these here are all in molar, moles per liter units. Now the change is minus X, and here's the thing. This is the molar solubility. So we're assuming all of this dissolves, right? Because that's what the question says. It says that much will dissolve in the water. So if all of that dissolves, what's left is 0 of that, because it all becomes ions in the end. Okay, so based on this question, we're saying that all of this has dissolved. So all of this has dissolved. And because all of it has dissolved, at the end, the solid has all become ions surrounded by water. So you no longer have just that solid. You have 0 of it left, and all of it has been converted to ions. And so what we're going to do here is, this is kind of all the side work to set up the ice table. Our official step 2 is writing a KSP. KSP is equal to the concentration of Pb2 plus times the concentration of I minus squared. Now, that's going to be equal to Pb concentration is X, and I concentration is 2X. But don't forget that is squared. So that's going to be X times, so 2 squared is 4, and then X squared is X squared, which is going to be equal to, so 4X squared times X is 4X to the power of 3, 4X cubed. And so all we really need to do is plug in our X value into that to find the KSP. So what is the X value? Well, let's take a look. The X value is actually just going to be our molar solubility. Because if you do this minus X and you get 0, X must be equal to this. So in a situation like this where you're given molar solubility, the X is going to be whatever your molar solubility was, because you're assuming you dissolve the whole thing. And again, KSP is based off that idea that you've dissolved the maximum amount that you can. And so we're going to write that down. We're going to write X is equal to MSP, which is equal to 3.731 times 10 to the power of negative 5 moles per liter. Now, just like any other equilibrium constant, you don't need to report units for the KSP. So let's go ahead and just plug that in. KSP is equal to 4x cubed, which is equal to 4 times 3.731 times 10 to the power of negative 5 cubed, which is equal to, so let's go ahead and do that. So this is to the power of 3. Times 4. And we get 2.0775 times 10 to the power of negative 13, or approximately how many sig figs do we need? 3 sig figs. 2.08 times 10 to the power of negative 13. So therefore, the KSP is approximately 2.08 times 10 to the power of negative 13. So let's go take a look at the question to recap what we just did. We were told that in this amount of water, or this volume of water, we could dissolve this much PbI2. And we want to know what the KSP is. So we're told what the maximum amount is you could dissolve in that water. And based on that maximum amount, we have to find what the KSP is, the equilibrium constant in this situation. So what we did is we wrote a dissociation equation, nice and balanced with our charges. We wrote some initial values out. And the ones that were easy to find were just the ion concentrations, because we know that before you dissolve, if you have pure water, there's no ions in there, so 0 and 0. We did the changes based off of the molar coefficients. So this is a 1 here, that's a 1 here as well. So we have plus x plus 2x, because as you add the solid, the ions will form. And this is a 2 over here because of the 2 over here. And then at the end, our equilibrium will be x and 2x here. And we also put a minus x over here because we know that since there's a 1 here, we're going to use that up and use it up based on the molar coefficient, minus x. Now, the issue was we didn't know what the initial values were or was, and so it was hard to find our equilibrium concentration. So the initial value for a question like this is actually the MSP. It's the molarity of the PbI2 once you kind of throw it into the water. So you have your MSP. We had to calculate that, and we did that using the concentration formula, and we got this value over here for the MSP, and so we use that, minus x, and we said that our equilibrium concentration is going to be 0. And so the reason for that is because we're assuming that this is the maximum that can and will dissolve. So if all of that dissolves, if all of the PbI2 dissolves, then at the end you have no more solid left. It all went to the ion side. So at equilibrium, you have it all dissolved, so we'd have 0 left over. And what that means is that the x must be equal to the MSP, because if MSP minus x is 0, well then x must be equal to MSP. Okay, and so that's what we mean by sometimes you can replace x by MSP. And so essentially what we did is once we found all this and set up our ice table, we made a KSP expression based on the equilibrium expression over here. And we replaced all the values by the x's, and we simplified to get the KSP is 4x cubed. We have our x value, which is our MSP. And what we did is we just plugged in the MSP, the x value, into the KSP expression, and then we solved to get the KSP, which is over here. So the KSP at this particular temperature, whatever it was, these conditions, is 2.08 times 10 to the power of negative 13, and this is to 2 or 3 significant figures. And the idea is that the higher the KSP, the more soluble something is, because if you think about it, that means your product is higher than whatever your solid was. So the higher the KSP, the more soluble something is. And there is a list of KSPs that you can actually take a look at, and I'll show you that in the next video. But if we go over here, this is a data table. It'll be posted in some area where your teacher keeps data sheets for you. It might be in a calendar or a Brightspace. But if you take a look here, we have different KSP values provided to us. And so those different KSP values are based off the MSP in a saturated solution where you dissolve the maximum that can dissolve. And so the higher the KSP, the more soluble your substance is, because it's more towards the right. The equilibrium favors the product, which is the ions. But the lower your KSP, like something very, very low, like negative 21 over here, that means your compound is not very soluble, because your equilibrium does not really favor the ions that much. It actually favors the solid a little bit more. So lower the KSP value, the lower the solubility. A higher KSP value, so let's say something like this negative 5 over here, means more soluble than something like this negative 21 over here. Okay, and so what we're going to do is we're going to take a look at, in this video, what we saw how to calculate the KSP using the MSP. In the next video, we're going to take a look at how can we figure out the MSP, what's the maximum that will dissolve, using the KSP values.